Ladies and gentlemen, dear colleagues, it's a great pleasure to introduce our first webinar series here from the Austrian platform of personalized medicine. My name is Barbara Obermayer-Pietsch, I'm the president, and I welcome you here in Graz from the Medical University and would like to introduce a very interesting topic to you. It's about sense and sensitivity. It's not Jane Austen's very famous story, but it's 21st century knowledge and its efficiency of computer-aided facial phenotyping in individuals with genetic syndromes. And now I call Berlin. I have the pleasure to introduce Martin Mensah from the Charité Berlin. Hello, Martin. And he will give us a very nice lecture on outstanding new technologies and on consequences, which are ethical, philosophical, and of course, medical and personalized medicine. So the floor is yours, Martin. Thank you very much.
Thank you. Thank you for giving me the great opportunity of presenting our data here in this webinar series. I want to talk about sense and sensitivity. There are new tools to automatically phenotype patients from ordinary photographs. And the question is whether it makes sense to use them. And the essential question is, what is the sensitivity of such tools? What is computer-aided facial phenotyping? Consider a patient with Down syndrome. When you encounter such a patient, you will immediately have an idea what to test in the patient. And that is because you might have, or most likely you will have already seen another patient featuring the very same syndrome. And because Down syndrome has a characteristic facial gestalt, it is possible to recognize the syndrome from the face. Based on this idea, Basil van der Get and colleagues suggested in 2016 to use computer facial recognition technology to suggest diagnosis in patients with genetic syndromes. You enter a photo, the computer, so the algorithm, we use Deep Gestalt, detects the face. It will process the facial features of the individual and analyze them by a deep neural network. That is, it will compare the biometry of your patient to a database of thousands of other images of patients featuring craniofacially dysmorphic genetic diseases. And then it will suggest a list of differential diagnoses. In this case, the computer suggested the correct diagnosis, Cornelia de Lange syndrome, as the most likely one, that is, on rank 1. We tested the system on several other images of individuals featuring genetic disorders. For example, on individuals having cleidocranial dysplasia. In this individual, for example, the correct diagnosis is suggested as the most likely one. Here is a boy who features Smith-Lemli-Opitz syndrome. And in this case as well, the system picks the correct diagnosis as the top suggestion. This woman is particularly interesting, for she does not feature an actual syndrome, but she carries a mutation that might cause a genetic syndrome. That is, she has a FGFR2 mutation, and this mutation is only mild, which means it's not fully penetrant. We only came across that variant, or we only detected it, because her son and her daughter, they feature Crouzon syndrome. I personally would consider her case to be absolutely inconspicuous and wouldn't suggest her having a genetic test at all. But because her children and grandchildren showed stronger features of Crouzon syndrome, we started genetic testing in the family, and then eventually we found that the causative mutation was inherited from her. We used her image to test Deep Gestalt as well, and we were surprised that the system picked the diagnosis, Crouzon dysostosis, in her, although she apparently features no, at least stark or strong facial features. It picked the diagnosis on rank 2, which is pretty well. So how can this be used to improve the diagnostics of rare diseases? To answer this question, you need to know how exomic, that is, genetic data, are currently processed. When we perform genetic tests these days, we do not only perform single gene testing, but we apply large gene panels or even entire exomes in the clinic. And these produce lots of data, and this data cannot be analyzed without the help of computers. So our pipelines invoke two sources of information classically. One is the signs and symptoms of the patient, and the other one is the genetic sequence, for example, an exome of the patient. We process these by symptom analysis or variant scoring, which is done automatically, and then we combine both scores to pick the correct diagnosis. This works pretty well, but everyone who does this kind of analysis knows that the pipelines that we use are certainly improvable and that their accuracy can be enhanced. So we suggested to additionally use a photo of the analyzed patient and to analyze this photo with pattern recognition software, for example, Deep Gestalt, and to add this into the diagnostic workflow, and by doing so, to enhance the diagnostic accuracy of the analysis of exome data. How do you have to imagine this? When we analyze an exome, we rate every variant that we see in the exome by scores, for example, by the cut score. If you have a mutation that is a pathogenic variant, one that causes a disease, here depicted in blue, you might rate this with a score of 30, which is pretty high. However, an exome usually carries neutral variants, non-pathogenic variants that are polymorphisms or just rare variants that do not cause any disorder. And some of them will acquire or will be rated with an even higher score by the usually used scoring systems. That means that when I analyze these data, I would first pick this gene, for it carries a variant that has a cut score that is nearly 40. So I would start with this one. I would check whether the gene is associated to a disease and whether that disease matches the phenotype of my patient. So whether the signs and symptoms I see in my patient are described with that disease. And I would find out they are not. So I would disregard this and I would say it's not the one. I would go for the next variant and check again. Is this variant associated with the disease? Does this disease match my patient's phenotype? And I would be disappointed. Only when I reached the fourth variant to be analyzed, I would be successful. And I would find that the variant that I'm currently analyzing and interpreting is actually the one that caused the disorder in my patient. However, this procedure is time and thus cost-consuming, and therefore it needs to be improved. When we improve it, we do this by invoking machine learning algorithms. How can that be done? We add an additional dimension to the analysis, a Gestalt score. That is a score that describes the similarity of the face of an analyzed patient to the average appearance of individuals featuring a certain disease that is associated with a gene that is depicted in this image. By doing so, we hope to be able to separate disease-causing variants and neutral variants on a better level. So the combination of scores should improve the prioritization procedure. You can see in this image that the variant that actually is disease-causing, the blue one, is now close or closer to the upper right corner of the image. That is, it is more likely to be disease-causing. Most of the red variants state on the y-axis and are not implied by the Gestalt score, therefore they can be easily ruled out. And some of the neutral variants also feature positive Gestalt scores. However, the combination of Gestalt score and variant score is not as strong as in the pathogenic variant. When you do such kind of an analysis, you plot not only the data of one patient, but of several patients to train your machine learning scores. And when we did this, we saw this. You can easily see that the pathogenic variants, that is all the blue variants labeled with the gene that carries them, are now plotted closer to the upper right corner, while the red variants are closer to the lower left corner. What is noteworthy is that I did not plot those variants that stayed on the axis, because they outnumber the pathogenic variants by several hundreds. And if I did so, I would just result in having here a bar, a red bar that consists or is made up of all these red dots. And another red bar would appear here. So this wouldn't give you any further information, therefore I left it out of the image. But still, the idea is easy to catch. When combining both scores, we are able to separate pathogenic from non-pathogenic variants. We did this using a support vector machine. That is a mathematical, statistical method that is frequently used in machine learning. And this support vector machine calculates a decision boundary. Based on the distribution of these dots that you see here, you can calculate the best boundary to decide whether a variant is pathogenic or not. This means that if a gene is plotted above this boundary, it is likely to carry a pathogenic variant. If it's plotted below the boundary, it is less likely to be pathogenic. And you can even go further. It is not only the question on which side of the boundary your gene is plotted, but the distance of a gene to that boundary is now a new and integrated measure for the likelihood of pathogenicity. Consider, for example, this FGFR2 mutation. The length of this vector is now the new measure for the likelihood of pathogenicity. So this is a new and integrated score that tells you whether you should consider a gene in your patient or not. The more different scores you combine and the more patients you have, so the greater your data is, the better this approach will work. We called the study the prioritization of exome data by image analysis, or in short, the PEDIA study. And we designed it as a multi-center study, collaborating with 53 international institutions. We included 679 patients who featured 105 monogenic different syndromes. And the aim was to improve the clinical interpretation of exome data. So how do the results of the PEDIA study look like? The ideal result would look like this. So we have a patient who features a pathogenic mutation in a gene, here depicted in purple, and who also has several non-pathogenic variants that are depicted here in this turquoise color. On the y-axis, you see the PEDIA score, the distance to the calculated decision boundary. And on the x-axis, you see the chromosomal position. So all the genes positioned on chromosome 1 would be here. Those on chromosome 2 are depicted here, 3, 4, 5, and so on. Here's the X chromosome, there's the Y chromosome, and at the very end, you'll find the mitochondrial chromosome. The height of these dots is the distance to the decision boundary. So this is the same vector you've seen in the figure earlier. And the idea is that now you can separate the pathogenic variant easily from the neutral variants, as in this picture. What are our general results? So this is what we've seen in our entire cohort. So this figure does not only plot a single individual, but 201 individuals. And I think what's easy to see is that the pathogenic variants plot into the upper part of this figure, while the neutral variants plot into the lower part. There's actually a bluish cloud down here consisting of all the neutral variants that were not implied by the PEDIA approach. Still, to be honest, some of the pathogenic variants showed negative PEDIA scores here, for example. This means that our approach is certainly further improvable. But however, we see that separation of neutral variants and pathogenic variants is strong when using the PEDIA score. Let's get back to the examples I've shown in the beginning of my presentation. So the boy who has Mensah syndrome, when we analyze this photo by deep gestalt, the correct diagnosis appears as the most likely one. When we perform a classical exome analysis, it would only appear on rank 11. But when we combine both, then it's the most likely variant to be checked. The Crouzon carrier. The woman had the correct diagnosis on rank 2 when using deep gestalt. It was on rank 3 when using a classical exome analysis approach. However, you have to bear in mind that that we would not have considered the FGFR2 mutation in her, even though it appeared in rank 3, if we had not known about her children featuring Crouzon syndrome. And when analyzing her using the PDA approach, the correct diagnosis or the correct gene is suggested as the most likely one. In the cleidocranial dysplasia example, the RANKS2 mutation causing cleidocranial dysplasia was only suggested as the 60th the 60th diagnosis. So we would never have found it, because usually in a normal clinical setting, we would not analyze the differential diagnosis lists until rank 60. When combining both, the correct diagnosis was on rank 35, which is better than a classical approach, but certainly further improvable. I could show more examples, but I want to summarize them. That's easier in a single figure. So here you see the sensitivity on the y-axis and the maximum rank that was considered on the x-axis. And what does sensitivity mean in this context? It means that we've found the correct diagnosis, or the correct diagnosis was suggested by the PDA approach on the respective rank that is indicated on the x-axis. So we compared the different approaches. In yellow, the deep gestalt approach, which means that we only analyzed the image, no further information. Then in green, we performed the classical exome analysis, meaning we analyzed exomic data and signs and symptoms. And in blue are the results of the PDA approach. The deep gestalt approach solved 17% of the cases on rank 1. So the top 1 sensitivity was 17%. What does this mean? It means in 17% of the cases in the PDA study, the correct diagnosis was suggested by deep gestalt as the most likely differential diagnosis in 17%. In 58%, we picked the correct gene as the most likely suggestion using a classical exome analysis approach. This is certainly better than just analyzing the image by deep gestalt, but frankly, that is not surprising. I would not have expected a facial image analysis tool to outperform exome sequencing. What we wanted to show is this. When we combined the classical exome sequencing approach with a gestalt analysis, we achieved a top 1 sensitivity of 91%, which was better than just performing a classical exome sequencing approach. When we did not consider only the first rank, but the first 10 ranks, the sensitivity increased accordingly. So in 99% of the cases, the PDA approach was able to pick the correct diagnosis of a given patient within the top 10 suggestions. What else could the tool be used to? There are other applications for facial recognition software in genetics and in the workup of patients with rare diseases. In 2018, there was a new gene discovered, or a new disease gene association was discovered. Donson mutations cause microcephaly, short stature, and lip abnormality disorder, or in short, MISLA. What is MISLA? MISLA is a disorder that is characterized by syndromic dwarfism, cell cycle disturbance, and radial ray defects. And this triad of symptoms is suggestive for another group of disorders, for Fanconi anemias. So initially, when MISLA was discovered, we were not sure whether it is actually a single disease entity or just a new subtype of Fanconi anemia. However, we thought that the patients who feature Johnson mutations have a characteristic face. This was just a hypothesis, and we needed to make an objective judgment on this. So we collected images of individuals featuring Johnson mutations. We built a control cohort of images of individuals featuring Fanconi anemia, and 3 further control cohorts, one featuring images of patients with various dysmorphic syndromes, another one featuring individuals who do not have a craniofacially dysmorphic disorder, and a 5th one with images of patients with Smith-Lemli-Opitz syndrome. And we analyzed these images using the deep Gestalt neural network. And the results are here. So to understand this plot, you need to know what the MCC is. It's Matthew's correlation coefficient. And I don't want to go into the mathematical details of this coefficient, but what you need to know is that when the MCC is around 0, it means that a classifier that is rated by this MCC is not better than a random decision. So you could use that classifier or flip a coin. Both would result in an MCC of 0. If the value is negative, it means that your classifier is worse than just flipping a coin, which means that the classifier mixes the classes up. So it takes FA for Missler or dysmorphic for Sloss and so on. If the classifier is, or if the MCC shows positive values, this means your classifier is actually pretty good. The maximum MCC is 1 and the minimum MCC is -1. And what you can see in this figure is that the MCC of Missler syndrome is pretty close to 1, which means that our assumption that Missler syndrome features a characteristic fasciist was confirmed by deep Gestalt. Interestingly, the group of inconspicuous controls also featured positive MCCs. This surprised us because deep Gestalt is not designed to detect an inconspicuous face. There is no model within the deep Gestalt neural network for the class inconspicuous face. Deep Gestalt solves a multi-class classification problem, and that multi-class classification problem is if you believe or if you think that your patient has a craniofacially dysmorphic syndrome, deep Gestalt will tell you which one it is. But if your patient has no craniofacially dysmorphic syndrome, deep Gestalt will be of poor use. So we were surprised to see this value, this high value in inconspicuous controls. This opens another question. How good is the diagnostic accuracy of deep Gestalt? So I just mentioned it. If you take an image of an individual not featuring a craniofacially dysmorphic syndrome, for example, an image of me, the system will, in any case, suggest differential diagnoses. In my case, for example, it suggests spinocerebellar ataxia and Angelman syndrome. Although I tend to laugh, well, I think it's not correct. So what did we do next? We took the hypothesis that, let's go back here. So when we analyzed this image, we saw that it suggested spinocerebellar ataxia in me. However, noteworthy is that here the value, the Gestalt score, is rather low. So we thought that it must be possible to pick images who do not, or that do not feature a craniofacially dysmorphic syndrome from those images that do. So we hypothesized that the Gestalt score in images of individuals with the syndrome is different from the Gestalt score of images of patients without a syndrome. We chose 17 different syndromes, and for each of these syndromes, we analyzed 19 photos. We matched these photos by age, sex, and ethnicity to control images, that is, images of individuals not featuring a craniofacially dysmorphic syndrome. So we ended up in total analyzing 646 images. Here you can see the distribution of the Gestalt score in the healthy control cohort. And what took me a little bit by surprise is that the scores actually differ among these individuals. So none of these individuals had a craniofacially dysmorphic syndrome. We evaluated these. So I asked my colleagues to have a look at the images, and we all agreed there's nothing in there in that image that would make us think of a certain syndrome. Still, the Gestalt score in this group varies. So it is not always low. Sometimes it's even higher than 0.8. The maximum Gestalt score would be 1.0. The lowest Gestalt score possible is 0. And we thought that the Gestalt scores of healthy individuals or inconspicuous images are low. They tend to be low, as you can see in the box plot, but they are not always low. And this is something one needs to bear in mind. When we compare them to the Gestalt scores of the syndromic control cohort, we do see that Gestalt scores of individuals featuring a syndrome are higher. They tend to be higher than those Gestalt scores of images not depicting individuals featuring a syndrome. But still, both box plots, both distributions overlap. So based on the Gestalt score only, it is impossible to accurately judge whether an individual has a syndrome at all. So you may use deep Gestalt to suggest or to aid finding the correct diagnosis if you're already sure that your patient is actually a genetic syndromic patient. But if you're not sure about this, deep Gestalt may bias your conclusion towards craniofacially dysmorphic syndromes because it will provide you with high Gestalt scores, even in individuals that do not feature any syndrome. However, this figure only depicts the maximum Gestalt score per case. And we wondered whether we could recalculate the output of deep Gestalt when we do not only invoke the top Gestalt score suggested, but the top 30 Gestalt scores of each case. We did this, again, I don't want to go into the mathematical details. We did this using a support vector machine, and we created a new measurement, a new score. Here it's called dysmorphology score. And this score is entirely based off deep Gestalt's output. So there's nothing in the score but the image of the patient. There's no sequence data in it. We do not give any further signs and symptoms to the system. It's just the image. But we use another method to calculate it. And when we do this, we can improve the separability of the two cohorts. So the syndromic cohort now is not overlapping that strongly anymore with the healthy cohort, but still there is overlap. So still this score too needs to be improved. Something else that we found about deep Gestalt when analyzing it with negative controls is that we were able to check its sensitivity, not only its specificity, not only its sensitivity. And we were surprised to see that some syndromes appeared more frequently in the suggested lists than others. For example, these syndromes appeared in more than 20% of the cases among the top 30 suggestions, these in more than 30%, those in more than 40, in more than 50, these even in more than 60, and those in more than 70%. And draw your attention to Angelman syndrome, which was also implied in my image. So that deep Gestalt thought I would have Angelman syndrome has nothing to do with my facial features. It also has nothing to do with me laughing on that image. It is because deep Gestalt has a bias towards that syndrome. And what we thought most interestingly is that the syndrome that appears most frequently is Fragile X, which is suggested in more than 80% of the healthy control images. In other words, if you upload an image and the person depicted on that image does not feature a syndrome at all, the chances that the system will suggest Fragile X among the suggestions list is more than 80%. In more than 4 out of 5 cases, it will suggest Fragile X. So much about deep gestalt and analyzing facial data. But in modern medical diagnostics, we also have other image data that are not mere ordinary photos, but that come from other sources, for example, radiograms. And we think that radiograms may be used as a further source of information. For example, consider these images. They all show malformed hands, and it's obvious that these hands feature malformations. However, it is more difficult to pick or to know the correct diagnosis. But the information needed to make the diagnosis is part of these images. It's completely in there. If you've seen the syndrome before, and if you've memorized its specific appearance in the hand, you will be able to diagnose these images. The first one shows Cook syndrome, as you can see from the distal phalanges. The second one shows syn polydactyly type 1, which is apparent from this additional phalangeal bones in the middle of the hand. The third one is Kettelmansky syndrome, because there's these supernumerary bone. And the last one is Gregg syndrome. It's a certain type of hexadactyly. So this, if you knew this in advance, you could have find this diagnosis directly. And we believe that equivalently to deep gestalt, it should be possible to train a neural network to classify these images and to tell a radiologist what rare disease is present in these images, even if the referring physician would not know this. So we aim to train a system using images of radiograms of hand malformations and a set of inconspicuous controls. And then once the system will run, the idea is that you enter a radiogram, bones will be detected, the bones will be measured, and they will be analyzed by a neural network that will classify them, that will suggest the correct diagnosis. To conclude, computer-aided facial phenotyping tools may simplify the diagnostic process of rare diseases. They all help. They can be invoked to interpret genetic test results. Think of the PEDIA study. They show a considerable sensitivity, but only a moderate specificity, which is mostly because they do not hold a model for the class inconspicuous face. And tools to classify radiograms are currently being developed. I thank you for your attention, and I thank Professor Obermayer-Pietsch for giving me the great opportunity of giving this talk today.
Thank you very much, Martin. This was really outstanding. So we have learned a lot. I would really have another look on the faces I see. So this is not only in rare diseases, but this might change our mindset about faces. So really great information and very nice research. And I have seen you have published a lot, so congratulations. We will now start the question and answer session. So the first question we got is, and some of them might have been answered already, where is the data set used for the program from? And is it open source, and how huge is it?
Okay, so there are different data sets. One is the data set that Deep Gestalt was trained on. And this belongs to the people who programmed Deep Gestalt. That's not me, but it's a startup, and they've created Deep Gestalt. You might have heard of Face2Gene, which is the application of Deep Gestalt. And the data is with them. Another data set, so it's not open source, but it's free to use. Another data set is the data set that we assembled in the PEDIA study. And we published this data set with the PEDIA study. However, due to data protection, to reasons of data protection, we cannot publish the images of our patients. So you might have recognized that in my talk, I always used an exemplary image because we cannot disclose these images. But what we can do is we can provide readers of our study with the statistical data. And this can be found in the appendix of the manuscript. Yep.
Very good, thank you. The next question would be, will this algorithm replace sequencing, and should it be used by general practitioners on every patient, like a mass screening?
So I think no. So one thing is it cannot replace sequencing because it's inferior to, its accuracy is inferior to sequencing. Think of the figure that we've provided in the PDF study. The yellow curve was the lowest, and the yellow curve showed the sensitivity of the image analysis tool only, and it was inferior to performing a classical sequencing approach. But what I do believe is that future tools to analyze exome data or sequence data will invoke facial images as well. Yeah, so there was a second part of the question.
Yeah, the next question is referring to that when first mentioning the Gestalt score. Can you please explain why you don't only use the Gestalt score? I think this is the same direction. For me, it looks like it would give you the same information as using both. Did I understand that wrong? So maybe this is in an early phase of the talk.
So the main reason for not only using Gestalt score is that the Gestalt score alone is not very specific. It is more specific than I would have thought, and I was also surprised. I was very surprised to see that it has a certain specificity and a certain sensitivity, but its accuracy is only moderate. If you only use the Gestalt score, you will end up with wrong diagnoses quite often. That's why the Gestalt score is currently only used as a diagnostic decision support system. And this is something I would strongly advise. If you use Deep Gestalt, then use it as a diagnostic support system. Do not use it to replace the judgment of a trained syndromologist, because a trained syndromologist will be better. However, the advantage of Deep Gestalt is that it provides us with an objective, reproducible measure of the facial appearance of an individual. So far, when I showed a photo of an individual featuring a certain disease, people would say, yeah, there's something about this face which makes me think of disease A, disorder B, syndrome C. But when we ask them to put this something into a word, they were like, yeah, it's a typical face for example, Down syndrome. And this typical face for this phrase is nothing you can objectively measure so far. Now with Deep Gestalt, you can. That's why we think it will improve the diagnostic process. Okay,
I think this is a very important point and puts out also how to use this tool. So the next question would be the graph syndromic versus healthy, where the healthy ones with high top 1 Gestalt score sequenced to find the new syndromic patients, and was the healthy categorization only done by clinicians looking at the image? So yeah. How were you sure to
There was a careful listener to my talk. It's true. We only judged them to be not syndromic by looking at the image by several clinicians. We did not sequence those individuals or the individuals that were depicted in the images that we used for a control cohort. However, most people do not feature a genetic syndrome. So collectively, genetic syndromes affect 5% of the population. And many of them feature characteristic facial appearances or have other signs and symptoms. So when we used an image of an individual that we thought did not feature a genetic syndrome, we thought so because of A, there was no distinctive characteristic in the face that made us think of a syndrome, and B, we did not have any information about the individual in that image to feature another symptom that is not shown in the face, for example, a heart defect or anything else. That's why we are pretty sure, although not absolutely sure, that the control cohort does not contain any individual featuring a genetic syndrome. But this is something you will never achieve, because even if we've sequenced them, we would not be able to rule out a genetic diagnosis. This is not how genetics works. We can use genetic sequencing to confirm a diagnosis, but we can never use it to rule something out.
The next question is really in the same direction. The question is, can this software also be used for other disorders, for example, endocrine disorders? So
yeah.
Would you be able to expand that from bone symptoms, bony faces to other things?
The answer is yes. So DeepGestalt is not the only tool for facial analysis. There are other tools, and I know some that were originally designed to actually detect endocrinological disorders in the patients. DeepGestalt is not limited to genetic causes for diseases, but it's analyzing any syndrome that is craniofacially dysmorphic. For example, there is a class for fetal alcohol disorder, which is not genetic, but still features certain facial appearances. So this can also be detected by DeepGestalt.
So next question is also what I would like to ask you. The facial recognition techniques may have some bias, so gender or racial bias. How about other ethnicities? All over the world it's the same. How is this accounted for in the algorithms you use?
So this is a very nice question, because we tested this in our papers, because we knew that image analysis software, not only when it comes to facial analysis, but also when, for example, there are tools to analyze the appearance of the skin for dermatologists, they are known to be biased by the ethnic background of the individual depicted. So what we did is we created subgroups. So we created different groups consisting of only individuals of a certain ethnic background. And then we tested the sensitivity and specificity of these groups only specific to the respective group. And we did not see major differences. This is something that changed. In the original, in the very first versions of DeepGestalt, there was a bias. For example, when you analyzed images of African babies featuring a Down syndrome, the tool was not able to pick the diagnosis to suggest it. And then the tool was retrained on a cohort, on a set of images of these babies, and now it can suggest the diagnosis. There's a very interesting paper from Lumaka and colleagues who analyzed this. And in the past 2 years, whenever we tested the system for biases regarding age, gender, or ethnicity, we did not find relevant differences in the results. So this is something the program fixed.
Okay, very interesting. Next question: is there a possibility and plan to add a control healthy class to the DeepGestalt system?
This is a question you need to answer. You need to ask the developer. In our paper, we suggest that they should do so. Whether they will, I cannot answer.
Okay. What camera is needed to get sufficient images to the facial recognition?
You can use a normal camera, just any camera. So it works, for example, also on a smartphone device. If you just if you just make a photo and that's it. So there are no special requirements. This is also, so there are no sophisticated requirements regarding lighting, positioning, resolution of the camera. The standard digital camera will be sufficient.
Okay, so the fantasy is that you cross the street and you're just catched by a camera nearby the lights, and then you're fixed as a syndrome. So that would be one of the dystopic ideas.
This is actually something that is not possible. Think of my image. So I would assume that my facial gestalt is inconspicuous, and still the system assigns me with a syndrome, which is utterly nonsense. But the system will do so in any image. That's why currently you cannot use the system to differentiate people who feature a syndrome from those who don't, even if you use the advanced approach that we describe in our current paper. The specificity of the tool is too poor for a screening approach.
Okay. So the next question is just in that direction also. If I look at some of my photos, I might also suggest a craniofacial disorder. However, on other pictures, I look stunning. So how do you exclude bias by the angle lightening of the photo itself?
So the idea is to use a frontal image. Ideally, you have a very frontal image, but it will work as long as both eyes are depicted on the image. So even if you are slightly turned to the side, it will still work. But once you have a total, once you only have the side of the hat, it will not work anymore. Currently, there is no research published on the influence of lighting and positioning on the results. But I know from the research we do that we did not find any major bias in these variables. But still, if in the normal situation would be, there is a patient, you take a photo, and normally you will be able to take a frontal photo of your patient.
Okay, so this has to be standardized somehow. The next question would be, could it be used for prenatal diagnosis?
It's a very good question, really good one. We also thought of this. For example, if you have a 3D ultrasound of an unborn, but so far, nobody tested this. And the question is, or the problem is, when you have the facial appearance of an unborn fetus, the facial appearance will differ from that of a born baby, because the baby is a bit older and it will be bigger. The facial appearances will differ. Therefore, it is possible. So I believe that if we just use the system on ultrasound scans, they will most likely suggest certain syndromes, because the system is not yet trained on images of unborns. But maybe it can be retrained. But this is an entirely open question, so nobody ever tackled this yet.
This is the first to the next question. Can the program be improved by feeding it more normal faces?
So we assume that the answer is yes. However, the developers tell us that they did not want the program to hold a class model of inconspicuous faces, because then this would impair the accuracy on the multi-class problem the tool is actually solving. So currently you use the tool after you yourself, as a human syndromologist, suggested a syndrome in the patient, not before anybody suggests a syndrome. And for this multi-class problem, it is a very good tool to give you an idea of what syndrome your patient actually features. If you retrain the model with several images of inconspicuous individuals, and you train a class for these images, then it's possible that the tool will suggest the class inconspicuous in individuals that feature only mild facial features. And this is a major hurdle in syndromology. So when we analyze patients without this tool, we also sometimes wonder, is there actually a characteristic facial appearance in the individual I'm currently examining? Or is this face totally normal? In some cases, the facial features are mild. And think, for example, of the woman with who was a croissant carrier. And if we train the system to detect or to classify inconspicuous faces, it's possible that in those cases, it will suggest inconspicuous, although they actually feature a syndrome or carry a mutation for a syndrome. That's why it's not only a scientific question whether or not to include this extra model of inconspicuous faces, but it will also affect, if it is done, the quality of the classification process.
This answers probably the next question. Is it possible to increase the specificity of the PEDIA, maybe by including more control subjects?
Certainly. So in the PEDIA study, we've used less than 1,000 images, and I'm absolutely sure if you use a larger cohort, you will get better results.
Next question is very interesting because it says that how do you deal with facial optimizing procedures in the age of tooth corrections in already young ages? How can this influence your results?
It's a good question. Think, for example, of Crouzon syndrome. So many of these patients are operated on at a very early age. And this means most of the images that exist of patients featuring Crouzon syndrome are actually of patients featuring Crouzon syndrome who were already operated on. That means the system itself is already trained on operated Crouzon syndromes. So maybe it's even less likely for the system to suggest a real unoperated Crouzon syndrome than a standard appearance of Crouzon syndrome, because most of the individuals nowadays are already operated. So this affects not only Crouzon syndrome, but any kind of syndrome. If a syndrome is treated early, and if this is the standard procedure of treating that syndrome, Deep Gestalt will be trained on images of comparable patients that were also treated. Therefore, it can detect the syndrome even in operated or treated patients.
We have a technical question. Could the results be better with three-dimensional data or with X-ray or MRI data? Would this add?
Yeah, there are other systems that use 3D information. We also wondered whether a 2D, so an ordinary image, is enough. However, the very data that I've presented show that Deep Gestalt's accuracy is pretty high, especially when combining it with classical sequencing approaches. So then the sensitivity is higher than 90%, reaching a top 10 sensitivity of 99%. In other words, the effort you need to take to create a 3D image does not account for the benefit or the increase in sensitivity you gain. It's just not worth it. When a patient comes to our ward and we would want to analyze them digitally, and it's easy to make a 2D image, but it's quite sophisticated to make a 3D image. As the 2D approach already shows the sensitivity higher than 90%, I don't think it's worth using a 3D approach.
The next question would be, you're starting by monogenetic diseases. What about multigenetic purposes? Because of course there is more than one gene, and how could you then also open up this approach to other disease groups, to other entities, endocrine disorders, etc.?
So Deep Gestalt or systems like Deep Gestalt will be able to analyze any disorder that features craniofacial dysmorphism without regard to the cause of that dysmorphism. When we use PEDIA, we designed a pipeline to analyze exome data, and currently all these pipelines work on monogenic models. That's why we limited the PEDIA approach to a cohort of monogenic diseases. When we will start analyzing individuals who feature polygenic diseases, we need other pipelines, not only the pipelines for the facial image analysis, but also other pipelines for the phenotype and the exome interpretation. And these pipelines are currently developed. But the standard pipelines at the moment are only able to pick monogenic diseases.
Okay. So we hope for the future for more data and more interesting presentations and ideas on that. I have a more philosophical question. How would you think about having craniofacial phenotypes caused by the genes? What is the link between these genes and the changes in these genes and the pathophysiology to have a certain facial appearance. How is it? It's crazy that it's so close to, or so near.
If you consider the face as an organ, then this organ consists of several tissues. There's muscle, there's bone, there's nervous tissue. My facial appearance depends on the shape of my brain inside my skull, and so on. So all these different tissues are developed or are regulated when they develop by several genes. And that's why several genetic disorders have an influence on the appearance of your face. So it's actually not that surprising that a genetic disorder affects your facial appearance, because the head and the face in particular is a very sophisticated product of the genetic information. And as this is the case, you will have an alteration in the facial appearance if you have an alteration in the genetic information.
So just to know about your future plans, what would be your next steps? What is your research going to, and what would you like to achieve in next years?
So our next projects are two projects. One is we want to compare the efficiency of Deep Gestalt to that of other facial phenotyping tools. Deep Gestalt is currently the most convenient to use and the most widely used system, but it's not the only system. And we wonder whether other systems are better, or whether the combination of different systems would improve the accuracy of the pipeline, and so on. So the next step will be, we will compare the different systems and their accuracy. And another thing that we are currently doing was shown in the very last slides. We want to develop a classifier to classify radiograms.
Okay. So it's very interesting. I wish you all the best for your future research, and many cooperations also. I hope that some of our persons in the auditorium would like to contact you. I think the email is quite visible. So thank you very much for this outstanding talk. And I would now like to close this session. So many thanks to... Okay, thank you so much. I would like to announce a few other webinars. You can find them on our website, on the ÖPPM website. So this is the webinar series. And I would like to thank you for your attention by mentioning that there are two other webinars till the end of this year. One is Public Perspectives on the donation and sharing of genomic and health information. Very, very interesting study by Richard Mann from Cambridge, UK. And this is presented by Barbara Preinsack. She's also a member of the board of the Austrian Platform for Personalized Medicine. And we will have then in early December the next webinar from an Austrian specialist. This will be about Gesundheitseconomy, and I'm very happy to welcome you again with all of our members and with the students, I suppose, that being in this webinar. So many thanks to you for your attention, and I will close this webinar, and we will see us at the ÖPPM next webinar series. Thank you. Thank you, Martin Mensah, for this very nice talk, and thank you for your attention. Thank you.